Welcome back, everybody. So let's take it from there after this cliffhanger. There is an analogy, in fact, in what we are doing. You might have heard that in order to scale up the batteries in electric cars, this is exactly the same idea. Plenty of small, cheap batteries, and in fact, this is what you have by now in electric cars. This is how you scale. So, in order to make it work, we are going to throw, I love throwing things away. Now you probably notice. So we are going to throw away the whole hierarchy with directories and files, flats. And we make the data model almost trivial, meaning that the cloud storage that we're going to have to store our gigantic data set is simply going to be what we call a key value model. It means that you have all of the files that now we are going to call them objects, billions, trillions of them, all they have is an ID, an identifier, right? And so if you have the ID, then you have the objects. So this is the data model. We are going to have key value models all over the place in this lecture, but this is one of them. This is an instance where we have the data modeling of the cloud storage that is almost trivial. And we get what we call a global key value model. I literally mean global, as in the whole planet, because this cloud storage, as is done by Amazon, Google, Microsoft Azure, and so on, is for the whole planet. It's a service. So how do we scale that? Because we need to actually make it happen. So if one machine is not good enough, there are a few tricks that you can try out. One of them could be, for example, if you are playing video games and it's not powerful enough, you just try to find a bigger machine, right? With more memory, more CPU, and so on, and even more and more and more. And in many cases, that kind of solves the problem. But you probably notice that it costs a lot of money, and the problem is that it keeps costing more and more and more money. Like every extra gigabyte that you add keeps getting more expensive. That's the problem with scaling up. So instead of scaling up, we can have an approach of scaling out, and now you know that this is what data centers do. Instead of trying to find a bigger machine, I just buy plenty more small machines, plenty, thousands, tens of thousands, millions if you have multiple data centers, billions. So that's called scaling out. Again, remember, scaling up, bigger machine, scaling out, more machines. The opposite of scaling up is scaling down. If you reduce, if you buy smaller machines, the opposite of scaling out is scaling in, if you reduce the number of machines, right? So scaling out, but there is a third way that is incredibly important that I will show you shortly. In this lecture, we will love to scale out. We love to have plenty more small machines. The reason is simple, it's the costs. Because the costs of more and more machines that are small is almost linear. Now, it's an oversimplification. If you run into a supply shortage, which actually happened in the previous years, then it might not be exactly linear if too many people want the machine, but it's more linear than scaling up, right? Scaling up, in fact, is not just that it's exponential, it's even hyperbolic. Hyperbolic in the sense that there's an asymptote. If you want today to give me a machine that has a petabyte of memory and a disk with 100 petabytes, that's going to probably cost you quintillions of dollars because it just doesn't exist. And the efforts that you would have to actually put into building that are so gigantic that I don't even think anybody on the planet has enough money to do it. So this is just showing you the limits of scaling up. But a petabyte of memory and 100 petabytes of storage in a data center, no problem at all. Just buy plenty of machines and you have that. And we have more than that, in fact, by scaling out. So this is why we are going to scale out a lot, plenty of small machines. But there is a third approach. And it's actually nice that ETH Juniors was here because there is, in that third approach, this is a very valuable insight for those of you who might be considering founding startups based on who wants to found a startup. Not so many yet. Maybe the idea is going to come to you in the coming years. I don't know, for some of you. The mistake that many people make is that they immediately think we are going to buy a lot of machines and go to the cloud and so on. But in fact, when you build the first prototype, it's worth trying to make it fit on your laptop because very often the data actually fits on your laptop. You can compress it, you can find ways, and you can make it faster just by writing better code. And this is much cheaper than going with scaling out or scaling up, right? So this is the reason why the first idea you should always have when it's not fast enough or there's not enough space, try to squeeze even more on a single machine. This is always the first thing you should think of. And there is this beautiful quote that I love: you can have a second computer once you've shown you know how to use the first one. You wouldn't imagine what you can get out of all of these laptops right here. Everything you can squeeze out of them. It's incredible just by learning all of these techniques. And I'll also show you a bit of that in the course. All right. But when we go big data and we reach petabyte scales, of course, that doesn't fit on a laptop. And here we need to scale out, and we'll have plenty of machines. So this is why we have data centers. Data centers are the way to scale out. So now you know, because majority of you answered the question correctly, we have in a data center tens of thousands of machines, typically. So it's boring. It's just rooms that are filled with machines. I put orders of magnitudes here. It's just with zeros, but it's approximate. There is kind of an upper bound for the number of machines in a data center that we consider to be around 100,000 machines. Beyond that, you need more data centers. You cannot keep them at the same location. The reason is actually very simple. It has to do with energy and cooling. Is that a data center like those that there are some in Zurich, by the way, in the north of Zurich, there is even some fiber optic ring around the city and some data centers. You might think it's in the mountains, right? There's these legends of all the data centers in the bunkers in the Swiss mountains, but they are also right here in Zurich. We went to a field trip actually a few years ago with the class and visited a data center. And they told us, you know, the energy that this consumes is that of an airport. The data center has the electricity bill of an airport. And if you reach 100,000, this is putting the system to its limit. And then you even start having issues with cooling down the whole thing, right? So this is a physical limit to what you can achieve. Of course, there are ways you can still try to do it efficiently, right? For example, at some places, you use the heat generated by the data center to heat apartments and flats for the towns or cities that are around. So you can use all of that, but you do have this physical limit with the number of machines, right? So think tens of thousands of machines in a data center. Now, in a single computer, I told you it's roughly your laptop, but actually it's a bit more than your laptop, slightly more than your laptop. You can have, I put 200, you know that it's all powers of 2 for the cores, right? Again, it's just an approximation. Let's say 128 cores that you could have on a machine, can be 64, 32, right? So this is the order of magnitude. So you see, it's not like millions of cores. It's just a 2 or 3 digit number of cores per machine, on each machine. In terms of storage, I already told you last week, we know how to build hard drives all the way to around 30 terabytes. I think 35 is on the agenda of some companies, but this is roughly the order of magnitude. That's typically what you fit on a single machine. In terms of RAM, you can have 16 gigabytes. That's still like your laptop. I think to date, the highest we can achieve is 6 terabytes on the same machine of working memory. So the working memory is the RAM. It looks like this. This is what disappears if you switch off the electricity, right? The one on top, if you switch off the electricity, it's still there. So this is long-term storage, and below it's short-term, just the working memory. All right, but this gives you the order of magnitude. What about the network? When you know that typically what you have at home is 1 gigabit, maybe 10 gigabits per second for some offerings. You can go all the way to 100 gigabits per second and maybe even sometimes more if you think of HPC, InfiniBand, and so on. So you can get a lot of bandwidth on a server, but it's still limited. And the fact that it's limited actually constrains the sort of things we can build in terms of big data systems, right? But you have the numbers, right? Now that you have in mind. Now, what does it look like? Well, even though I told you we are just buying thousands of these machines, what you have in a data center is not just 1,000 desks with a desktop computer on each desk, right? In fact, what you do instead is that you pile up the computers on top of each other in towers that look just like this. This is called a rack. And every single layer that you see in there See, so this is the rack. Every layer here is a machine, right? So you pile the machine up on top of each other. You can have maybe, I don't know, 10 or 20 machines piled up on top of each other, and then plenty of racks. And then you have a room, and then you have another room with, again, plenty of racks, but it looks like this. There is a standardization, of course, of all of that because there are multiple providers, but they standardize the height so that it can be assembled with modularity, right? So this is called the rack unit, RU, and then that's typically 2 or 4 rack units is the height of one of them. Now, I said these are computers. It doesn't have to be computers. You can also have pure disks. So one layer is just going to have 10 disks, for example, or you can have one layer that is just made of network switches, so network cables that are to dispatch over the network. Routers is the name. So this is very modular, and it's like a Lego game. You basically build your racks and put in whatever you need. So typically, I think in the same rack, you might have like a couple of machines, and maybe below you're going to have a couple of layers of hard drives, and maybe, I don't know, at the top or below a network router that connects to the rest of the data center, right? All modular. So this is what there is. This is an example of rack server. In fact, I have one in my office. The problem is that we moved to another building, and this is extremely heavy. So I don't manage anymore to transport it all by myself. But this is what it looks like. So a single layer, a single server. Right, and you can find them, by the way, you can find them on some online shops if you want to see the specifications. There's a link on the course module if you want to see what it looks like. Okay, so this is what there is in a data center. So now I demystified it. Now you know. Maybe some of you who was already in a data center. Some of you? Okay, so you already know. But maybe some the others, you will have an opportunity one day to visit one. It's very, very impressive. Okay, so now let's move on to cloud storage. One of them, because now you know that there's Amazon, there's Google, and there's Microsoft. So the big three, there's also some other players, but these are the main three. Now, who is surprised to see Amazon here? Some of you. Because a couple of years ago, some people were surprised, like, what is a bookshop doing in a big data lecture? And what actually happened is that, yes, it was a bookshop. Amazon was pretty much selling books, but they had a problem around the busy periods, like Christmas and so on, that suddenly they didn't have enough computers. And so they needed to buy computers in order to be able to continue selling over the Christmas periods. The problem is that once they did that, the rest of the year, the computers were wasted because they were unused. And then they had the idea of renting them. If we don't use the resources, why don't we rent the resources to everybody else, and they can use the cores and the memory and so on. And this is how a whole new subdivision was born, known as Amazon Web Services, or AWS. And this is why now Amazon is one of the biggest players in terms of cloud services. That was basically born of that, of renting out the unused space. Now they are no longer alone. There's Google Cloud, there's Microsoft Azure, and so on. So there's plenty of players out there. But this is the market. So what's funny about them, the cloud players, is that they more or less have the same offering. It just has different names. There might be a bit some differences in the details of the products. So whenever I tell you about one of them, for example, Amazon S3, you'll have the same thing on Azure, and you'll have the same thing in Google Cloud, right? Google Cloud Storage, Microsoft Azure Blob Storage, Azure Data Lake, and so on. So they all have these offerings. But S3 was the first one of its kind in terms of cloud services. So I'm going to show it to you. In fact, what I, at the same time, don't like and like about S3, so let's start with what I don't like. I have no idea what it's made of, because that's not public. So it's basically just an API and a service that you can use, but we don't know how it's implemented. Why do I like that? Is that for teaching, it's great. Because I told you about data independence. Whenever you learn something, you first need to understand it seen from outside with the way you use it, and only then you go inside. In every week, almost, I'm going to do that. I'm first going to explain seen from outside, and then I tell you what there is inside. S3, I have no choice because I don't know what's inside, so it forces me to explain it to you from outside. So here's the model. In S3, it's a global cloud service you have so-called buckets. And in the buckets, you have, so they are identified with bucket IDs, and in the buckets, you have objects. The objects are your files, and that's it. That's the model behind S3. Now, what are these objects? There can be CSV files, XML files, JSON files, but that wasn't the first idea. The first idea was that these objects could be pictures, videos, and so on. In fact, that kind of storage is used by all the providers that allow you to upload your photos, I don't know, Apple, Google, and so on. Behind, this is what there is. There is ultimately a cloud service like that, where each photo is an object, each video is an object. It even goes further than that. If you consider providers like Netflix, Amazon Prime, Disney Plus, and so on, pretty sure a lot of you probably watch some, like to watch some series. This is also where it's stored. So what happens when you have the latest Star Trek that you want to offer as a SVOD? What you do is that you cut it into chunks of a few seconds, the whole series. So you have 5 seconds, 5 seconds, 5 seconds, 5 seconds in different resolutions. And you store them as objects. So every 5 seconds, just an ID, 5 seconds is an order of magnitude, corresponds to one object. What does streaming mean? It means that you download 5 seconds and then 5 seconds and then 5 seconds as you watch the series. If you don't have enough internet speed, you start downloading the lower resolution 5 seconds that take less space, or you switch back to high resolution. But this is all supported by cloud storage like that. In fact, if some of you have firewalls or monitors on your laptop, you will see Amazon, Google, and Microsoft Azure addresses in the background when you actually do this, because this is all stored in the end over there, right? So it's used for pictures, videos, and so on, but also for file backups when the backup services also rely on this. The encrypted storage often relies on these services as well. And also big data, because of course, one day the data scientists discovered that this actually is also great to store data, XML, JSON, CSV, and so on. And we'll see how for this course, it also works great. All right, so we have buckets, and in the buckets, we have the objects. So if you have the ID of the bucket plus the ID of the object, then you can retrieve the object that you're interested in. You can also upload an object with a new ID and so on. Now, it's interesting to know the limits, because I told you your use case. It's videos, pictures, and so on. So the limit of the size of an object is 5 terabytes. 5 terabytes. It cannot be bigger than that. There are no buckets inside buckets. I'll come back on the hierarchy. There are no buckets inside buckets, to answer your question on only one level. Yeah?
So the question is, are buckets inside buckets?
Exactly. So there are no buckets inside buckets. It's completely excluded. You cannot nest at all, right? But I'll come back on the hierarchy because there are a few things to say about that. So maximum 5 terabytes. There is a maximum of 100 buckets that you can create. It's just to limit abuse. In fact, if you politely write a message to the support and ask for more, they might give you more. But there is by default this limit of 100 buckets for one account, right? So think of a bucket as a way to organize your objects, right? By what you want to do, right? So this is how it's used. All right, now let's do a bit of law, URA, legal services. When you are a company and you have customers that use your services, you want to have a contract between the two parties because they are paying you money and they want something in exchange for money and they want guarantees in exchange for money. So the guarantees in terms of cloud services, they are usually expressed with plenty of nines that look like this. So the contracts are full of nines. So what do they mean? There's plenty of things they can mean. In that case, it's about durability. A typical durability is expressed as 99.999999999%. It means that every year, one object in 100 billion is lost for whatever reason. Maybe a hard drive crashed or the redundancy didn't work and so on. But you lose one object every 100 billion. So most customers do not have that many objects. So it's unlikely they will ever lose something. But nevertheless, it's not going to be 100% because this is just real life. So what you have in your contract is a digit like that that says it's 99.99999, and you know that 1 year there is a risk of losing one object. If this is an unacceptable threshold because you do have many objects, then store it twice, for example, and then you can work on the probability. But then this is as the customer. All right? Then there are other numbers that do not express durability, they express the availability of the service. For example, you might have in the contract, these are just examples here, that the service is available 99.99% of the time. If you compute that over a year, it means that you might have 1 hour of downtime every year. It might crash, be unavailable for 1 hour. If you change so it's all about nines. If you change the number of nines, you basically get these orders of magnitudes, right? So 99% is 4 days of outage a year, all the way to 99.99999, which is 4 seconds every year, right? And again, these things happen. You probably heard it in the news when it happens. For example, when the Swisscom network suddenly becomes unavailable and so on. So, right, this is real life. These things happen, but you can quantify them and try to put limits or guarantees on the duration of an outage. Okay, and again, it's all expressed with nines. SLA at the top means service level agreements. That's the name of the documents that you get whenever you use a service. And if you use it, then you agree with the service level agreements. All right. Again, something, it's only indicative because in the case of S3, it's more like 300 milliseconds than 10 milliseconds. And I think even in the in the case of S3, you do not get a guarantee on that. So again, this is just an example unrelated to S3. What about the guarantee on the response time? Like if you request something, how much time do you wait until you get it? Well, they could tell you, okay, on average, it's going to take 10 milliseconds, but that's not what they do. In fact, the way they do it is that they guarantee you a specific amount, for example, 10 milliseconds, in so and so many % of the cases. So an example could be, we guarantee you you're going to get an answer below 10 milliseconds of waiting time, but maybe once in 1,000 cases, that's going to take longer, right? And you put a limit on the % of cases where that might actually take longer. We don't like average or median. We really try to look at percentiles for this. Again, I repeat, 10 milliseconds is not the response time of S3. If you want something in your mind, it's more like a few 100 milliseconds of the typical response time for cloud storage. All right, so far so good. Everybody following? Okay. So this is the service level agreements, the legalese, if you want to call it legalese. Now we have something that is known as the CAP theorem. That is true not only for S3, it's true of any cloud service, any distributed service related to data. It's an impossibility triangle. It basically says you would like this and that, but you can't have it. You can only have 2 of the 3, but you cannot have the 3 at the same time. So what are the this, and that? It's C, A, and P actually. So they mean C for consistency, A for availability, and P for partition tolerance. And what the CAP theorem tells us is you can't have all 3. You have to make a choice. You have to give up on one of these. So now I'm going to explain to you what they mean. So atomic consistency, so the C, consistency, it's not the same thing as in ACID. This is why I put this atomic in parentheses. It's not the same consistency as in ACID. What we mean here with consistency in the context of a distributed service with data is that you might have 100 machines, 100 nodes, or 1,000 nodes that are able to serve the data, because if you have millions of people connected, it cannot be the same machine for everybody, right? So this is spread over the machines. Maybe, I don't know, you have 1,000 customers on each one of the 1,000 machines, making it 1 million in total. But in that case, Atomic consistency means it doesn't matter with which machine you're speaking, they all give you the same thing. They all see the same data. So if you request the 5 seconds, the first 5 seconds of the first episode of the 3rd season of Star Trek Discovery, it doesn't matter which computer you are asking for it, you get the exact same 5 seconds. That's called consistency. You might not have consistency if, depending on the machine with which you connect, you might get something different. Then it's not consistent, right? So this is the C. Then there is the A. The A means the system is available, meaning you connect to it, and it gives you an answer in a reasonable amount of time. Like, for example, in the cloud storage, you would expect like 300 milliseconds. Then it's available. Not available means you try to connect to it, but it hangs or it tells you, no, sorry, I'm not available right now. Please come back in an hour, right? Your customers are very important to us, but please come back in an hour. So this is not available. Available means you connect, you get an answer. So that's the A of CAP. And why don't I have, do I have P? I think I introduce it like this, the P, so partition tolerance. So here's the P. You have a network of machines, all the computers that are connected with network cables in the data center. They are connected with each other. Since they are serving the customers, they might have some copy of the data available, or they can transmit it over the network. Now, imagine that somewhere there is an update. For example, somebody wrote a comment on LinkedIn. So the comment is uploaded over there with the computer, and then there is an update. There's the new comments. Now it has to propagate all over, right? Because the other nodes have to start accessing that web. So ideally, it would propagate to the whole network of machines, and at some point, they all have the same view. But the problem is that sort of things can happen. You might have a network cable that breaks. You might have, I don't know, an earthquake. You might have a fire. You might have something that happens. And the network is partitioned. The network is partitioned. It means that you have part of the network on the left, part of the network on the right, but they cannot speak to each other anymore. So this is called the partition of the network. Partition tolerance means that when that happens, the system can still continue to work. So it means that maybe, I don't know, this is North America on the left and this is Asia on the right, and maybe in North America, they will connect to the nodes on the left. In Asia, they will connect to the nodes on the right, and it works, right? Then it's called partition tolerance. However, right here, you see that it's not consistent in that case. Because the people in North America, they will see the new version. The people in Asia, they won't. They will see an older version. So it means that in that case, it's partition tolerant, it's available, but it's not consistent because you don't see the same thing at the two places. Now, this is called a AP system, available partition tolerant. You also have CP or PC systems that are tolerant to the partition tolerance, to the partition of the network, but they will just stop being available. They will be consistent, but they will stop serving for a while, maybe for the duration of the partition, and then when it reconnects, they are available again, but they are consistent. At no point in time do they give inconsistent answers. That's called a CP system. And finally, we have AC or CA, depending on the orders. CA means it's available and consistent, but if the network partitions, that's it. It crashes and bam, that's gone. So it's not partition tolerant.
So there's another question. Mm-hmm. So how long between the updates between nodes to consider we have consistency?
So the way I would formulate it in terms of the duration is consistency means hypothetically at the same time. So two people at the same time connect to the nodes. Do they see the same data at the same time? So it's independent of the duration of the change, right? You connect at the same time. Do you see or not the same data? Now, if you are a theoretical physicist, you can argue, yes, 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 but since Einstein, we know that it's impossible, that everything is at the same time and so on. But we are on Earth, and it's small enough that we don't see this kind of effect. So if you could go there starting arguing with nanoseconds and so on, but this is just beyond what we are interested in big data, right? So this is the way to look at it. Yes, if you connect to a node.
But if I connect to node A and someone connects at node B, the data should be propagated.
Oh, yes, but then if you connect to a node, let me try to understand your thinking. So I think maybe you are focused on my slide right here when I show you the propagation. The propagation, actually, I only showed it to you in order to illustrate why you cannot have C, A, and P. But basically, if you forget about this graph for a moment, you forget about this graph. What it means is a system can choose to be partition tolerant. It means that if there is a partition of the network, it's not going to crash. It will continue to function properly. But if the network is partitioned, you have to make a choice between two things if you want to be partition tolerant. Either you say, for the duration of the network partition, I make myself unavailable. And then once the network partition stops, I propagate all of my updates, and then everybody is consistent again. Or second option, you say, I'm partition tolerant, I'm not going to crash, but I'm going to remain available. The cost of that is that people on one side and people on the other side might have, for a while, for the duration of the network partition, different version of the same data. Now, the question that you are asking, I think, when you ask about the propagation of the data over the network, and you query at some node A, and then it propagates to some node B, and do you see the same thing? What you have in mind is the normal function without network partition, right? Because then there's no partition of the network. But then the way to reason about it is more that if you want to be consistent, you, at every update, block for a little while the delivery of the data until it has propagated, and then you start serving again. But it's not going to be considered unavailable at that point. It's just that it takes a bit more time until this is done. So now I'm not entirely sure if I answered your original question or not. If I didn't, we can take it offline. I did? Awesome, perfect. So for whom does that make sense? CAP? Okay, awesome. So either you are CP or CA or AP. Now, beware, 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 because now I see a proliferation of scientific papers by all the big players claiming to be CA and P. Do not let yourself be convinced by that. You need to think critically. The reason they are doing that, it's marketing. They want to market it as, oh, we are CA and P, we are partition tolerant, consistent, and available. It's a mental trick. In fact, the reasoning is that if network partitions are very rare, so rare that we don't care about them, then of course we're always A and C, right? But the thing is, the day that there is a network partition, then they will have to make a choice. Either they crash, or they become unavailable, or they become inconsistent. But you have to make a choice. You cannot be all three at the same time. All right, so that's the CAP theorem. All right, and in the case of S3, I don't actually know what they are because they say they are CA and P, but that basically means they won't tell you what happens if there is a network partition. Maybe one day there is one, and then we will know. Okay, so next part, that's called the REST API. Who already heard of REST? Who never heard of REST? Who heard of HTTP? Okay, then you've heard of REST, because REST is actually HTTP, but let me explain. So, when you have a service, can be S3, later it can be HDFS, MapReduce, MongoDB, like any service, you have to offer a way to connect to it. You might do it on the shell, You open a shell and then you start writing stuff. Or you might have a Jupyter notebook. That's also quite a convenient way of doing that, especially for teaching. Or you might expose it as an API through some programming language. Then you write in Java, R, or C++, and so on, Python. Or you expose it to REST. REST means you go through the web, through the HTTP protocol. The web was invented here in Switzerland in 1989 by Sir Tim Berners-Lee at CERN in Geneva. And I don't need to introduce it to you anymore because it's so famous. But I can say a few words about the underlying way that the web works. And the idea is that you type this in your address bar, right? So this is a URL, Universal Resource Locator. And the idea is that it's a web page. So what you can have through these addresses are web pages, pictures, and so on. But it turns out that this is not the only thing you can send over with these addresses. You can also send XML, JSON, CSV. The idea of the web originally is it's humans talking to machines. You sit in front of a browser, you connect to a machine and get a web page. So it's between a human and a machine. REST is a generalization of this from machine to machine. Instead of a human using this address, it's a machine, it's a program. This is called a resource, these addresses right here. We tend to call them URIs, Universal Resource Identifiers. You might have heard of URLs, URNs, URI, IRIs, and so on. I think I'm going to just call them URI for the duration of the lecture. I should say IRI, but nobody says IRI, so we just continue to say URI. URL, URN, I think, doesn't exist anymore. That was dropped, so the distinction between the two was dropped, so there's only one kind of them. HTTP is one way that they could start with. That's the one we use in the browsers. You also have FTP, mail-to, and so on and so on. So there are actually other schemes, but this is called a scheme. Then we have an authority. That's the domains you can buy. You pay a two-digit number of francs every year, and then you can have your own domain like this. Then you have a path with the slashes, //////. Then you might have a question mark for a query that is in particular used for when you fill a form, for example, or parameters for the page. And then a fragment with the sharp. All the URIs look like this: scheme, authority, path, query, fragments. For the lecture, I think we're just going to have HTTP all over the place because that's kind of the one that has established itself, but it doesn't necessarily mean that it's going over the web, right? But we'll come back to that later. Now, in the case of S3, there is a REST API. It means that you can access the objects and the buckets with resources like this, with URIs. On the top, you have an example of bucket URI, where you have the name of the bucket in orange. You need to replace it with the actual name, .s3, blah, blah, blah. So in green, that would be the location of the data center. And at the bottom, you have the URI of an object, right? So you have the bucket ID in the domain, and you have the object name after the slash, right? There is also an alternate scheme called S3, where you directly say //bucket/object name. This, of course, your browser will not understand, but if you use some tool in the ecosystem of S3, then the tools will actually understand the S3 scheme as well. It's just equivalent to the HTTP one. So that's half of the web. In the web, HTTP, every resource is identified with a URI, an image, a video, a document, even abstract things can be identified with resources. A light bulb can be identified with a resource. And the second part is the methods. Once you have a resource, you can get it, you can put it, meaning you upload data, you can delete it, then when you try to get it again, it's gone, or you can post something, it means you interact with it in some way. Getting means that you're not modifying anything. A side effect would mean that something changes, right? But get doesn't modify anything. You just politely ask to download a representation of the resource, an image, a video, a data set. That's get. You can get an object, you can get a bucket, so list the contents of a bucket in that case. Then you can put an object somewhere, but you need to know the URI for that. So you put an object at a specific URI. It's idempotent. What does idempotent mean? It means that if you do it twice, it's no different from doing it once, right? So if you put the same thing twice to some place, then it's as if you had put it only once. So put works that way. If you do a get after a put, you should get the same thing that you've just put, right? That's kind of logical. Delete means that you request that the resource becomes unavailable, so you get the 404. Who heard of 404? Everybody knows 404, right? That's the not found. So if you do a delete and try a get after that, you should get a 404 after that. Post is the kind of the everything else kind of method. Imagine, for example, the most common use case is you want to upload an object, but you don't know its ID yet. You don't know its URI yet. For example, you have a calendar and you have an API for the calendar, a REST API. You want to create a calendar entry, but you don't have any URI yet. Then you use post. And post will give you a URI. And then you can use the URI to interact with it, right? So post is the most generic one, but it can have side effects and so on. So that's also the most dangerous one. And that's it. So basically, once you know the bucket URIs and the object URIs, you can interact with S3 with put, delete, get, all the REST API. Right? There are many other ways to interact with S3, but the REST API is one of them. Now, somebody asked earlier, that was a very good question, can you have a bucket in a bucket in a bucket in a bucket? The answer is no, you can't. In cloud storage like this, object storage, there is no hierarchy. There are no directories, absolutely nothing. But you can cheat and pretend that there is a hierarchy. This is exactly what S3 is doing. So you see all of these object IDs here. These are all object IDs. You see the slashes? As a human being, it looks like this, right? It looks like there are directories and so on. That's only in your mind. S3 couldn't care less about the slashes. The slashes are just characters like any other to S3. So there is no hierarchy. But you can pretend and say, okay, if there's a slash, I, as a human, pretend that it's a directory. And in fact, if you connect to the S3 interface over the web, you will see these nice displays with the directories and so on, and you can organize your data sets with the directories. But do not forget that S3 doesn't care about them and doesn't know about them. It's a simulation of hierarchy, but it's not a real hierarchy. For whom does that make sense? Right. Another thing, and I'm going to end on that one, you can use S3 to host websites. In fact, it's the cheapest way to host a website that is purely static, meaning nothing changes, no interaction, it's just pages that don't move. That's the cheapest way, be it Azure, it can also be the same on Azure and Google, but basically this is very cheap to host a website. The JSONic website, we have the JSONic language throughout the semester, is in fact hosted on S3, very cheap. Okay, so I'm going to end right here. Just before you go, I like to check that you followed. So just, if you give me 30 more seconds to just ask you this. This is basically just a way for me to know if I'm too fast, I'm too slow, I should accelerate, I should slow down. So it's just a way for me to get an impression. And after that, you're good to go. So my goal is the 80 to 99% bucket. This means that the speed is right. Okay. If you understood less, you know that we are here, I'm here, the TA team is here, you have the exercises, so we are here to interact. Eiffel is also here, but it doesn't mean that we are not here too, of course. Oh, this is perfectly symmetrical. All right, so we have people who understand everything. We have most of you who understood 80%. Thank you very much, everybody. The exercises on SQL, please do not forget to do them. This is how you learn. And there is also a small JSONic tutorial because by popular request, I'm spreading JSONic all over the semester to just do it chunk by chunk. Thank you very much, everybody. Have a great week ahead, and I'll see you next Tuesday at 8 a.m. Thank you.